Hello everyone. So this is day 2 of our 30 days 30 deep learning projects challenge. So let's get started. Today is classify handwritten digits using a simple neural network on MNIST. We have done this problem in our previous challenge of doing 30 machine learning projects in 30 days, but today we will be doing it with the help of a very simple neural network. So let's get started. The flow is going to be same. I will go and use the ChatGPT to help me out with code and everything, and then we will be asking questions. So here it is. uh, Hey, today is day 2 of today is day 2 of the challenge, and here is the problem statement. Okay, so we are going to use the MNIST dataset. It is one of the most popular dataset for learning the basics of machine learning and neural network. It contains handwritten digits. Our goal is to build neural network and then classify these digits. We will be using simple neural network for this task. We have used this in our previous day 1 problem as well. Let's break down the solution into easy to follow steps, and I will explain every part so you understand what is happening. We will use Keras and a high level API in TensorFlow to make this as simple as possible. So first we will be loading the MNIST data. Let me go, and I have already linked it. This is going to be the data. So this is the data set. I will go and download it. Let me see if where can I get this data from. Yes, so I will go and download this data set. To see the data, you need to sign in. Okay, so I need to sign in. I'll go and sign in from my Gmail account. I think now I should be able to download the dataset. Can I download the dataset? Yes, I can download the dataset. This is the image and the label. I'll go and download the dataset and then come back and read it. Then we will prepare and process the data, build this simple feed forward neural network, and then train it and compile it, evaluate the model performance, and then we will make the predictions. Very easy. We have done this on day number 1. So we are going to replicate it what we have done on day 1, and also we have, I guess, understood in depth about this sequential, what this means and how it functions, what is the meaning of dense and flatten. So we saw, we I guess we did see the meaning of sequential, but we did not see this dense and flatten layers. So today we are going to explore that. We have downloaded the data set, and then we will be using matplot library to visualize by plotting a graph. So yes, let's get started. I will go and then do what? So I'll go click on open in and the terminal. Yes. So we'll go and simply use this terminal to run our code. So what we are going to do, first of all, move the data set that we have downloaded from the downloads folder. It was it was simple submission to dataset folder, and then once done we are going to look at it. This is the image id and label, so this is the dataset, and I will call it as simple submission, or what I can call, I can rename it. Let me go and refactor it, rename it to day 2, day 2 csv. Okay, so what I'll do, I'll, you know what, do what, and I'll move this thing here, and then I'll start coding. So the problem I do want to mention in the file itself, that the problem title is this, and uh, data set is, where have we downloaded the data set from? The data set we have downloaded from this Kaggle problem. Now let's get started. Let's import all the libraries. So import what? Let me go back here. Import all the libraries. So we are going to import NumPy for doing the operations on arrays, like numerical operations, and then import the TensorFlow as, hang on, as TensorFlow. Then we will import, okay, it says that we can import it from this data set. Do you think should we go and import this? Let me see what the data set is from this TensorFlow. Keras datasets import from, import MNIST from TensorFlow Keras models import sequential model. We have understood in depth what it, how it works, like what it is in day one problem. Layers import dense layer and a flattened layer, and then we will import matplot as pl matplot pyplot as pld. So done. Yes. So before that, what I want to do, I want to check in day one. We saw one type of layer only, dense. Now we are going to see the other type of layer as well, which is flattened. One, we have imported all the libraries. Let's go and load all the libraries. I will say I want to load the libraries. I want to see the data. So can we use data frame for uh, better visualization? Okay. Okay, so we have loaded. So let's go what? Let's go back to this thing and load the MNIST database. So we are going to load the data. So we are going to load the data from, we'll say X train, X Y train, and then we will have X validation data, Y validation data we will be using for validation, and we will be using from MNIST dot load data. I want to check the data, print X train dot shape. Let's go and run this Python day 2 and do what, maximize it a little, and it has downloaded the data, and this is the shape of the data. Now I want to do what, I want to see the shape of X train we just saw, right? X validation. uh, this is the X validation. I want to see the data. So what we are going to do, before that I want to see the data. Mhm. So it says that the I want to remove, I want to get away with this warning. So I'll go and use, I am getting this warning. How do I get away with it? So it says I will have to install this thing. So it says the warning you're seeing is related to the URL library 3 and library SSL3, which means that the version of SSL being used incompatible with this. So for that, what we need to do, there are few ways to handle this. The simplest way to resolve this warning is to downgrade you. Okay, so we are downgrading it, and now let me run this code again. Do I see any warning? Let me see. I don't see any warning. So what I'll do, see the shape of all the variables that we have created. Okay, now let's run the code file again, and this is the shapes. We have 60,000 28 by 28 images. We have 60,000 the the value, target value, whether they I mean the result, what does the image represent, 0 1 2 3 4 5, and then we have 10,000 for the validation, the image of the 28 by 28 size, and then this is the y well shape, which is the result for those training train images used for training data. So but I want to see, how do I see? So before doing that, we what we want to do, we want to flatten the images. One more thing, because I remember if I go here and do what, uh, okay, I'll go here. What we before transitioning it into a data frame, we are flattening the images. The images are of, you saw that the images are of size 28 by 28, which results in 784. So we are going to flatten it because each image has these many pictures. So why are we flattening it? I'll say, why are we flattening images? This is so that the model can understand it better. So it says, uh, flattening the images is an essential part for preparing the data to work with a fully connected, dense neural network. Let me explain why we do it and how it affects the neural network. The MNIST images are originally represented in 28 by 28 format, which means each image is a 28 pixel by 28 pixel grid. In terms of data, each MNIST image is represented as a 2D array. Okay, with 28 rows and 28 columns containing pixel values from 0 to 20 to 55. Let me go and see the data here. Okay, image ID. Oh, so this was the label. Okay. So this was not the full output, right? Hang on. Correct. So in terms of data, each MNIST image is represented as a 2D array. We saw that. Now neural network expects 1D array. That is why we are flattening it. Uh, Neural network expects 1D array. So we flatten the 28 into 28 pixel image into 784 1D array vector. Now let's go and see, is this what ChatGPT is also trying to explain? So a fully connected layer in neural network expects that input to be in 1D array format. A fully connected layer means every neuron in one layer is connected to every neuron in the next layer. Since the images are 28 by 28 2D arrays, we need to transform them into single 1D array containing all the pixel values from before feeding them into a dense neural network layer. And how do we do that? 28 by 28 is 784 pixels. So we are going to have one single row having 784 fixed pixel values. Okay. In CNN, this is not needed, but we will not study about that for now because we will do what? We will get confused, and the basic idea of solving one problem one day is to not get overwhelmed with the whole concepts, right? So let's get back. We have understood why we are flattening it, because the neural network expects 1D array. It is in 2D array of 22 by 22 size. So we flatten it. How do we flatten it? So we say we are going to reshape it, and we are going to reshape it into 1D array from this command. So it is going to be x train flat x train flat x train dot re- reshape and minus 128 by 28. I want to see this. What is the, I want to see, did they explain it here? The Yes, how do we reshape it? We reshape it with the help of this function. Now it changes the shape of the training data. Here minus 1 is used to infer the number of samples. Okay. And 28 by 28 flattens the image into a vector of 784 pixel. Okay. Let's do what? X validation flat x validation dot reshape minus 128 by 28. Let's go and run it again, and I'll go what? Hide it. That's done. Once done, what we are going to do, we are going to go back to the thingy here, not this one. Yes. So we have loaded the data. Um, okay. Yes. So I will convert this data into data frame, and this is convert the x train and y train into data frames for better visualization. Okay. Now we'll do what? X train, and this is data frame is going to be, we will need to import the data library first. Import pandas as pd, and we'll say pd dot data frame x train flat x validation data frame panda and then it is going to be, so we are getting this y y trained data frame, and this is one dimensional. So we will do what, we will use series, and here we will say the thing is going to be y train, and the label of this 1D series is going to be target target name, sorry, in label. Let me go and print this x train df, print this y train df, the head, and let's clear the terminal, run it. This is how it is looking. This is looking like, so yes, see, this is the 784 columns, flatten images. This is the output. The first image represents 5 number, the second 0 number, third row represents fourth number, the fourth row represents 1 number, and the fifth row represents 9 number. So this is how it is looking. We are able to see how it looks. Now we'll go back to our previous things. So the step one was, yeah, step two was to load the images. So I'll go back here. Step two is load the data. And step number, this is step number three, pre-process the prepare and pre-process the data. Step number 4 is what? Build the neural network. So it was explaining it very nicely why we are doing it, right? So now we are going to do what? Build the neural network. So we have come back here. We in the day number one we saw why we are using sequential model, because it builds layers in sequences, and from the input of one layer is the output of the previous layer. And we do specify the activation, which is rectified linear unit. It helps in deciding which neuron to turn on or which neuron to turn off for the better output, for predicting the better result. And then yeah, so this is, and then we also learned, if you remember, why do we go ahead with these 128, 64, and this number. If you see, uh, yeah, if you see, mostly it is in the power of 2. So we saw that also, we learned that also. And we saw that we do specify the input shape in the first layer, and then in the following layers, in the next layers, we do not specify that, because the input of one layer is the output from the previous layer. So yes, um, we use sequential to stack layers one after the another. So what we'll do, we'll create model using sequential, and then we will do what, add layers. We start with 128, which is the first hidden layer, with the rectified linear unit activation function. The input shape is going to be what, 784. Why? Because the size of one image, the row columns are going to be 784, 28 multiplied by 28. That's how we have flattened it, right? And then yes, so let's build that. Model dot add a dense layer, we will add. And how many output units we want, neurons we want 128 neurons. And then activation function is going to be rectified linear unit. and then the input shape is going to be an array of 784, sorry, 784, this. Once done, then we will add the second layer, and then the second layer will be what, the half of that, which is 64, 64. And the activation function is going to be again rectified linear unit. And then the output layer, let's come back here. 64 neurons, the output layer will have 10 neurons. 10 neurons how? Because we have to predict out of 10 digits. Yes, so 0 to 9. So that is why 10 neurons as output. Now, in why are we going ahead with a different activation? Because it is used to turn the output into probabilities with sum equal to 1. Okay. So it says that it is this activation function is used to output into probabilities, like one has what probability. So we have all the 10 neurons, and each 10 neurons will have the probability, and the sum of all the probability of sum of the probability of all the 10 neurons will equal to 1. So that is why we are using this softmax. So we'll add the final layer, which will have 10 neurons, and the activation function is going to be softmax. And softmax activation function, because yes, I want to do this. Will the output layer will have 10. Okay, just a second. Yeah, let me keep it here. Yeah, so the activation function, the output layer has 10 neurons, each representing one of the digits. And then we will also specify why we are going ahead with using this activation function. So we have understood that it will print the probability of each number. Now we'll do what? Step number 5 is, sorry, I had fever. I still have the mucus thing going on. Compile the model. So we will do model.compile, and then we need to specify a couple of things, like what would be the optimizer. We will go ahead with the same optimizer as we have used, and we have also learned in the prerequisites that I have asked the Kaggle courses, that what is the meaning of this admin optimizer. And to revisit again, it is a popular choice for training deep learning models. We have used a different loss and metric in the day one problem. Here it is different. So we are using categorical cross entropy, since we have multiple categories 0 to 9 to predict. Sparse is used since our labels are integers rather than one hot encoded vectors. Okay, so it says that categorical cross entropy is used because we have a category to predict, right? And then sparse is used because we have exact labels, not one hot encoded vectors. If you remember, we have been solving multiple problems. We know what one hot encoding is. So then we are going to use accuracy as metric to track the model's performance. This is what it does is, basically with each iteration it uses these combinations, this Adam optimizer, to optimize the, the neurons, this optimize such that the loss becomes maximum minimum, and how it is going, and the way it calculates the model performance is accuracy. So it optimizes that. So what we do, the loss is sparse. I need to copy it. Sparse, I'll copy, not copy, sparse categorical cross entropy CROSS entropy, and then we are going to use the metrics is going to be accuracy. That's it. And then we what we'll do, step number 6 is train the model. So if you have been following this post or my day one video, you know that I've asked you to go and finish couple of very basic courses from Kaggle. uh, and there you Kaggle, like introduction to machine learning, deep learning, and convolutional neural network. There it has the Kaggle. They have the author has clearly explained that when the model is training it, we can store everything in the history, right? History variable. So we are training on the x-train y-train, and then we are specifying this is the data, that the unseen data it has to validate. uh, so evaluate the performance on this unseen data, and how many iterations it has to run. We say that it has to run 10 iterations. Like with each iteration it will in within each iteration it is going to take a batch size of 32 samples, and then it is going to do what, it is going to evaluate the performance, make sure that the loss is coming low, and then generate the prediction, and that is how it is going to train the model and then perform the same thing on the validation data. So and then we want to see everything it is doing within each epoch, within each iteration. So we do that by passing verbose equals to 1, that is print information during the training. So we'll do what, we and then we will save it inside the history variable. So model dot fit, we'll do what, model dot fit x train flat, hang on, why is it not using the flat thing? Oh, they are resaving it, yes. So we need to train it on the flat variable, and then the y validation, okay, and then the validation split, not validation data, is going to be x validation flat and y validation. They were one series, so we do not have to flatten them. Then epochs are 10, batch size is 32, and verbose, yes, we want to see the result. Once done, we will come back and evaluate the performance. Now, step number 7 is evaluate the model. Now, we'll come back here and evaluate the model. We will evaluate the model by using what? By using this model dot evaluate function. We will evaluate on the x validation flat and y validation, correct, and then we will save it in the, we will save what, we will save what, the loss and accuracy, validation loss, validation accuracy, validation loss and validation accuracy, and then we will print the validation data accuracy is validation accuracy. So we have evaluated the model of performance. Now what we are going to see, we are going to see how it looks, the validation and everything, the law, how it looks. So we will do step number 8, and we will do what? Visualize the training and performance. Yeah, validation performance. So we'll do what? We create a history data frame. We will do panda dot data frame and history dot history. It is saved in the history. And history data frame, we have got in the history data frame, we have got accuracy, and then validation, accuracy, and then we are simply going to plot it. And then the X label is going to be epochs for each iteration, how it is performing. The Y label is going to be accuracy, sorry, and the title is going to be training and validation accuracy. Training and validation accuracy, and then we will simply show it. That's all. Now we are going to do what? We are going to run the code, and we have an error on line number 42. It says, hang on, here I made mistake. Why? That's why the Y train. Run it again. Now it should not. Yes, it is working fine. In the first epoch, this is how it is performing. In the first epoch, we had the loss of 1.31, accuracy of 0.83. The accuracy is keep getting better. The loss is keep getting poor, minimum, and this is how it is giving us the graph. If you see that here, the loss, here the accuracy is represented by the blue line. The accuracy is like this, and the loss is here. And if we need to understand which epoch is the best, we need to see where the accuracy of the uh, where the uh, loss of the validation data should not increase, and there we need to stop. So this is for the accuracy. If we want to print for the and loss, let me see this will work or not. I mean, I could have easily printed what is there in the history data frame and see if there is any what columns with loss and everything. Here you see the it is getting decreased, so we could have stopped here, or it is increasing now, so we could have stopped this. This seems a better epoch for me, but the more I'll go deep, the better. I'll keep on seeing that, oh, it is increasing further, so I'll stick with 10, but I'll go and change the loss here. Here it is loss, here it is loss, and run it again. So this is the loss. I'll go. This is the loss. So this is how the model is performing. We can go and test it on what? We can go and test it on a sample image. So we will go and create an image, and then we can go and predict how it is doing. So what we'll do, we are going to predict make prediction on the first five images. So we are going to take the unseen images, which is from the X validation, the five images, and from for each image we are going to do what? We are going to predict it. And then from 1 to 5, what we will do, we will plot, display each of the test images, retrieve the predicted label for each image, and then show the true label. So the title is predicted this and true is this. Okay, so let's do what? Step number 9. Hang on. Make some prediction. We are doing prediction on some first five test images, the validate images from the validation data. Predictions and model dot predict on X validation first five images, and for I in range uh, 5, we'll do what? Plot image show X validation this image, and we will reshape it in 20 by 28 size. And how do we show it? In gray. And then we will, the title is going to be, we'll say predicted. What have we predicted? We have predicted, we want to, so if you remember, we used softmax as the activation function for our output, and it tells us about the prediction for each number. Now we are going to get the maximum prediction, and we are going to say this is what the model has predicted this image to be. So we are going to get this from this argmax from predictions of this. For this row it will output 10 neurons, 10 predictions, and get the prediction, the maximum prediction. Return that it has predicted that, and the true value is y validation this I location I. I'm really sorry. Axis of, and then TLT show. Let's go and rerun this file again to see what it will print. This is the loss, and we have error 56. Where do we have the, don't you think I should flat? It was expecting 784, and I gave it a 28 by 28 vector. So I think now it should work. Hmm. Let's go back here and see. We have error at line number 60. So it has no. It be flattened. Let's run it again and see if this time it will not work. I'll see how to print it. Oh, so it predicted 7 and the true image was also 7. So I'll go take the screenshot. Predicted 2, original was true. Wow. Predicted 5, original was 5. Wow. Predicted 2, original was true. 0. And here also it has predicted really well. So the model is performing really good. Model is performing really good. So I'm really happy with how the model is performing. The accuracy is coming as this. The accuracy is coming as 96%, which is really good. This is how we have coded. Just to review back, we have used sequential model, and then we have used this. We did not use it. I don't know why we have imported MNIST data frame directly from the TensorFlow .keras datasets package, and then we saw how it looks using the pandas data frame. Then we use sequential, we use dense layers, we use activation function rectified linear unit, and then for the output we use 10 neurons, a layer with 10 neurons, and the activation function we used was softmax. Why did we use it? We use it because it outputs into probabilities. So the 10 neurons are going to have the probability, and the sum of all those probability is going to be 1, and we are going to predict as the neuron with the maximum predict probability. Then we have used optimizer as add-in. The loss function that we have used here for our optimization for compiling is sparse categorical cross entropy. Why? Because this is a categorical classification, which is classifying from 0 to 9 digits, and sparse because this is numbers, it's 0 to 9, not one hot encoding columns, right? Then we train the model using the fit function, where we specify the training and the flattened images. We do specify what is the validation data that we have to optimize against the performance of the model. We went ahead with using 10 epochs, and the that is the iterations. And then we decided to go ahead with the 32 samples within each epochs as the batch size. We wanted to see the output, so we set the verbose as 1. Then we evaluated the model. We saw the performance of the accuracy of the model is coming as 96%, which is really good. Let me go and output it. here. Okay, now the we also visualize the loss and the accuracy with the help of matplot library from the history variable, and convert before that we converted it into data frame. We also made prediction on the first five images from the unseen validation data, and we saw that it has correctly predicted all the images. So all in all, the model is working really good. Now I'll go do what? I'll go and commit this thing, and here day 2, add code for day 2, and once I mean, it should be available here. I can go and check here that the code is there on the git repository, so it should be available for you guys as well. I'll go and publish this recording me coding this problem on the YouTube channel. You guys can go and check out. Also, you will see the textual representation of the code and what we did and how we did on this tech journal. So thank you very much. We'll come back on day 3 to solve another I mean, do another project. So thank you very much.